Alright, 38. So 38 is a pretty straightforward conservation of energy problem using this new form of gravitational potential energy right here. The only issue that I had when I first read the problem was, if you read it, it says if the probe was launched with an initial energy of 5 times 10 to the 7 joules. I thought, excuse me, I thought reading that was the initial total energy, but um, the book was thinking that was implying that this is the initial kinetic energy. So that could be a little confusing. At least for me it was. So, hypothetical planet 0. So we'll just call the mass of this planet mass of planet 0. I'll just label some of the givens here. 5 e to the 23 kilograms. The radius of 0 is 3 e to the 6 meters. Alright, so let's get right into part A. Part A is asking us to find the kinetic energy at this farther distance out from the center. So conservation energy initial equals energy final. We start off with U gravity initial potential, gravitational potential plus kinetic initial equals gravitational potential final plus kinetic energy final. And we know that UGI, I'll just write it over here. This is negative G, your mass, times the mass of the planet, mz, over the radius of the planet squared, plus, now this is given, they said the initial energy is 5 e to the 7 joules. And then we have a new position farther out at 4 e to the 6 meters, and we're going to square that. Don't forget. Oh! Shoot, sorry. This is not force. This is energy. Whoopsie. My bad. See, typically students have the opposite problem. They'll forget to square the force. My problem was I inadvertently squared the energy, which is not a good thing. Alright, so we know oh, they also give us the mass of the probe to be launched. Little m is 10 kilograms. So we know all this. We know all this. This is really just negative g times 10 times 5e to the 23 over 3e, 3e to the 6 plus 5e to the 7 equals negative g times 10 times 5e to the 23 over 4 e to the 6 plus KEF. Solve for KEF, because everything here, these are all just numbers that we know. KEF equals 2.22 e to the 7 joules. So we lose, as you should be able to reason out, if you're going up higher, you're gaining potential energy, which means due to conservation of energy, we would have had to have lost energy. as you can lost kinetic energy, and so as you can see, we started with 5 times 10 to the 7 joules of kinetic energy, dropped down to 2.2 times 10 to the 7, so a little less than half. Part B wants us to, if the probe is to achieve a maximum distance of 8 times 10 to the 6 meters, what initial kinetic energy must it be launched from the surface? So that just means, like, maximum distance means it comes to a stop, which means this term is 0. So really, it's just UGI plus KEI equals UGF, and we're looking for KEI. So this becomes negative, this is the same as before, negative G times 10. Don't forget that potential energy gravitationally is negative, as we discussed in the notes, and don't forget to not square that. Over 3e to the 6 plus KE initial, what we're looking for, equals negative G times 10, 3 over, what was it, 8 e to the 6 meters. So solve for KEI and you get 6.95 times 10 to the 7 joules. A good bit more than what we had in this case. Alright, so that was a pretty straightforward problem. The next problem is going to be dealing with centripetal force and all that stuff. So, alright, see ya.